Hello, welcome back. Alright, I'm gonna re-up the Discord link because it's a pet peeve of mine when it doesn't show me the preview in Discord. Oh, I still get that little broken video. Darn. Hate it when it gives me that icon instead of the load screen. I gotta let it circulate for a minute before I click the copy link button. Okay, welcome. Today we're going to have a few less viewers than usual because some of the senior design folks are heading out for a tour relatively soon here. Okay. So I'm going to give everybody a minute to fan on in while I find where I'm at here. I think we left off on the IPv4 Datagram's header, but we'll back up one slide so everyone remembers where we're at. Okay, so when we last left off, we were talking about what a unit of data is at the network layer. So we learned that on the link layer, it's a frame. Okay, well, on the network layer, typically we call it a datagram, although if I'm going to be honest with you guys, I've never heard anybody call it a datagram outside of academia. I've heard most people call it an IP packet, an Internet Protocol packet. It's definitely the more common term. However, as you will see later on, Java calls it a datagram. So it's important for you to remember that it's called a datagram so that when you think about what you need to type to get your code done in Java, you remember, oh yeah, everything relating to this kind of thing is called datagram. The whole library is called datagram. So Java tries to follow the standard, not the common parlance. And also the datagram functionality has been in Java for a long time, and perhaps people used to call them datagrams back in the day. I'm sure that in many circles, people still call them datagrams. All right, I mentioned that we will be discussing IPv4 primarily instead of IPv6. Part of it's for historical reasons. Part of it's because IPv4 is still the predominant protocol on the internet. Most of it is just because IPv6 is really hard to discuss because the addresses are so long. So you might have seen in the homework that you have to get the IPv6 address. You might have seen what mine is like. It's this giant thing. It's expressed in 4-byte with separated by semicolon characters. So 4 hex characters and then separated by colons. And you got 8 of those guys. It's extremely long, so it's just too hard to work with. IP addresses, IPv4 addresses, to their credit, are nice and short. So let's look at the IPv4 datagram. I'll try to figure out what's in this header here. We got 20 bytes, so just a little bit more than the Ethernet frame, right, which had the 6-byte destination, 6-byte source, and 2-byte type. And remember that type usually corresponded to this, to IPv4 or IPv6 or a different network layer protocol. As it turns out, IP ended up dominating network layer protocols just like Ethernet ended up dominating link layer protocols. So they ended up kind of having those 2 bytes for nothing. They probably could have gotten away with just 1 because the overwhelming majority of Ethernet frames have that field set as IPv4 or IPv6, and there are not enough other options to justify the use of 2 bytes. And we'll see a lot more of that here in the IPv4 header. We'll see a lot of planning ahead. Remember, this was developed in the 70s and 80s. A lot of planning ahead that ended up not coming to fruition or ended up becoming obsolete or simply not being used because it's less useful than they thought it would be, or it was superseded by something else. And so we'll see IPv6, which was a development basically of the last decade, or perhaps the last 2 decades if you go back to its really early versions. IPv6, much more streamlined, much better header. A lot of this stuff gets ultimately removed. So we'll talk about some of that too. All right, so the first part there, and I'm just doing this in blocks, so if we go back here, you see that spanning across a whole row here, that's 32 bits, right? So 32 divided by 8 is 4-ish, yeah, sounds like it, 4. So we're looking at 4 bytes. Okay, version, again, tells us if it's IPv4 or IPv6. So you might go, well, isn't that just a duplication of what we saw in the Ethernet frames type field? Why don't we just use that? Good question. I don't know. I think they had planned for the Ethernet type field to tell you that it was IP, and then you would discover if it was v4 or v6 here. That might have been the original plan. Honestly, not sure what the plan was there. Yeah, this is pretty much a duplication of a field we already have, but it's short. But again, we're adding overhead. Maybe they thought there would be more types as well besides 4 and 6. Who knows? Header length. So there are optional fields at the end of the header. Again, I'm going to go back for a second, and you'll see that there's the options extras down there. Now, it's possible that you have options, which means that this field, the header length field, will point to the address of the first byte of data. So it'll tell you on which byte does the data start. And so that could be a number anywhere from, however long this is without the options, right? So it could just say 21. That would be the default because there are 20 bytes in the header. So byte 21 would be the first byte of data. Or if there are other options, it could be, 42 or 54. It depends how long the options run. All right, so that tells you what the first byte of data is. The type of service, we talked about how you can get different quality of service for different kinds of traffic. So this type of service field was designed for that, to designate what kind of traffic this is. So you could say something like, this is my ultra super high priority network traffic, or you could say something like, just give me your best effort here. The problem is that the sending machine gets to decide what to put here. So of course you could just flag all of your traffic as super important, and of course everybody on the internet could flag all of their traffic as super important. It would be the equivalent of all mail being designated priority mail, which, surprise, surprise, it kind of is, isn't it? Pretty much all mail is sent at the same priority level today. But to an extent, the type of service field is still in use. There are some routers and networks that'll listen to it. For the most part, though, it's not used too much today. And then you've got your datagram length field. Notice the typo there from where I copied this from. Datagram length. Anyway, the datagram length field is the header plus the data length in bytes. So we already had a header length field before that tells us where the data starts. This field tells us how long the whole packet is going to be. So remember that this is one of the first things to come in because things arrive in order at the NIC. And so this allows the NIC to know when this message will end. So that's a very nice thing for it to be able to do, to anticipate how long it's going to be. This is also useful when you're sending a very large message. So IP supports a transmission of up to 65, etc. bytes, 2 to the 16th bytes. Whereas, as we remember, the Ethernet frame only holds 1480, 1500 plus the 20 byte header. So how does it hold so many bytes? Well, it doesn't. They have to be split up over multiple datagrams in that case, right? And we'll see how that happens in a bit. So most datagrams are much smaller than the maximum size. Generally, the maximum is not used at all. We usually think of the maximum as the max that'll fit into an Ethernet frame. So remember, we've got 20 bytes of header here, and then we've got 1480 and change to work with in the Ethernet frame. And so that leaves us with something like 1460 bytes of payload to work with total here in the IP datagram. And I'll let you work out the exact math yourself on a quiz or a test or something at some point. I don't know. I'll integrate that somewhere. Maybe we'll do it on the lab. All right, the next row, next 32-bit row. So you've got your 16-bit identifier, then some flags, and then a fragmentation offset. And notice that not everything here is an even byte size. That's why I have this in 32-bit rows. This is usually how it's portrayed, right? It's very explicit here that the fragmentation offset is 13 bits. That's not an even multiple of 8, right? And so there's a 16-bit identifier, then 3 bits of flags, and then 13 bits of fragmentation offset. So we'll see that a lot here, that everything's not exactly an even multiple of bytes. So these fields allow IPv4 to split a large chunk of data along several datagrams. So this was used to transmit if you had a message that you wanted to send, but it was too big to fit inside the payload of the Ethernet frame, which again, 1500 byte max minus what's used for the headers. And not every NIC can even accept that. Some NICs can only accept smaller Ethernet frames. Then you would have to split it up over several datagrams. And so fragmentation allowed a router that knew that the next router in the path couldn't accept a datagram of the size that it wanted to send to split it up. And IPv6 doesn't use fragmentation at all. You'll also be hard-pressed to find that many devices that use fragmentation on IPv4 today, because fragmentation adds overhead to the router. It causes the router to have to split the packet up, which means it has to regenerate it into different datagrams, compute the identifier, compute the flags, compute the offsets. That's overhead. And remember, the router's main concern is switching as fast as possible. So what a lot of modern routers will do is, instead of bothering to fragment your data, they will just drop the packet and send you back a message that said, hey, this didn't fit, try again. Or someone along the path couldn't take a message this big, try again. That puts less overhead on the router, more overhead on the host machine. And you can also fragment outside the router. You can fragment at the host machine. But at that point, what's the difference between, say, doing that and sending multiple datagrams? Why don't you just send multiple datagrams and reconstruct it in your application? So doing it at the host machine is exceptionally pointless. But all right. Let's say that you've decided to split it. Let's look at how it works. So let's say a datagram is split. It's given a unique ID that goes in that identifier. So for example, let's say it's 123. Obviously it's a 16-bit binary, but let's just say it's 123. And then the flags are pretty straightforward. A 1 for there's more data on the way. This is not the last fragment. A 0 for this is the last fragment. Then you have your offset, which is insert data starting at this byte. All right, so the first datagram obviously has an offset of 0 since you're starting the data from the beginning, from 0. And then the other datagrams beyond that are 0 plus however many bytes of data that you've transmitted so far. So once you've transmitted 1,000 bytes, it would be 1,000 or 1,001. All right, so let's look at an example. The host sends a datagram with a 5,000 byte payload, so it clearly doesn't fit. We'll say that the router knows the next link has we call this a maximum transmission unit, or an MTU, that the link can handle in an individual frame of 1,500, so a standard Ethernet frame. So the router will split this into 4 fragments. Okay, by splitting it into 4 fragments, we now have 4 headers instead of 1, as compared to this imaginary datagram that had the 5,000 bytes in the payload and just 1 header and just 1 datagram. So by splitting it into 4 parts, we've incurred an extra 60 bytes of overhead, an extra 3 headers. The payload of each header, the payload of each datagram can be 1,480 bytes. Remember, we lost 20 for the header. The MTU is 1,500. So fragment 1 has an ID of 123. We set the flag to 1 to indicate there are more on the way. This is the last one. The offset starts at 0. The next fragment has the same ID. We set the flag to 1 because there's still more on the way. And the offset is going to be 185. Why 185? Because the offset is given in bytes. Bytes are 8 bits. So if you transmitted, 8-byte chunks. So a byte is 8 bits, and then we designate the offset in 8-byte chunks. This is a little bit more complicated. You can consider it like a super byte. Like 8 bytes makes a byte chunk or something, whatever you want to call it. 1480 divided by 8 is 185. So we indicate the offset as 185. The reason they do this is because there's not that much room for an offset. If you wanted to have a large number, like 1480, you would need to make a larger offset. So they just decided, well, we'll just do it in 8s, since bytes are in 8s anyway. So another space-saving decision. All right, the next one comes in. ID 123, flag 1 again, because there's still more on the way. Now we're at 370 because 180 times 2, you get 370. And then the last fragment comes in at 123. Now we set the flag to 0 because this is the last one, and now the offset is 555. And so the total size there, 580 bytes in that last packet, right? Because there's 5,000 minus the 1480 times 3 that we've sent, and then plus 20 for its header. So the last transmission, the last datagram, isn't full. The last datagram is just 580 bytes big at that point. Okay, so again, not used particularly often. Let's go on to something that is used quite often, backbone of a lot of internet traffic, the time to live field. You would think, just by looking at it, that this isn't particularly useful, but it happens to be fundamentally essential. In fact, so essential that it's interesting that it's not in the Ethernet frame. So in either chat, as we discuss it, why don't you add why you think it's not in the Ethernet frame? So the time to live is simple. Every time a router gets a packet, it reads the time to live field. If it sees a 0 there, it discards it. Or rather, first it subtracts 1. If it gets a 0, it discards it. It does something else, typically, as it discards it. We'll talk about that more later. But every router that gets a datagram subtracts 1 from the time to live field and then passes it along or discards it if it's reached 0. And the effect of that is that no packets can bounce around in the network forever if it's lost. This means that no packet can be lost forever and consume precious network resources by bouncing around eternally. So if there wasn't a time to live field and there was some sort of routing issue, remember routing is basically a graph theory problem. So if there was some kind of routing issue that caused a packet to bounce from place to place, let's say it went from A to B to C to D to E to F and then back to A again, and it just repeated this journey over and over and over again. Well, obviously, if a lot of packets start to do that, it adds up, and it'll eventually consume all the resources of the network in this infinite loop. This makes sure that no packet can ever infinitely loop indefinitely. It will eventually just be discarded somewhere along the way. So the amount of danger that can be caused by a misrouted packet is quite low. So why don't we have this in Ethernet? Why don't we have it at the link layer? We'll come back to that if no one's answered it. Okay, the next thing you see in this row is the protocol. And again, I do want to emphasize these aren't really rows. These are just 32-bit blocks that are separated into rows for your convenience. This is just another 32 bits following the last one. So next you get the protocol. This is the same thing as the type field in Ethernet. It's telling you what you're going to see at the next layer. So we haven't learned about the transport layer yet, but when we do, you'll have to reference back to here. Protocol is what's on the next layer. So same thing as the type in the Ethernet field. It tells you what you're going to be getting in your payload. And then we have a checksum. So a checksum is another form of error checking, but it's simpler than the CRC. And the reason that it's simpler is because your operating system doesn't have dedicated hardware for computing error checking. Your hardware is able to compute the CRC near instantly because it's tailor-made for that. Your operating system is a generic computing machine. Your computer is a generic computing machine. It does all kinds of stuff, and it's not exceptionally good at any kind of math. It's decent at addition. That's one of the things it's best at. And so a checksum uses addition. You use a simple addition. You convert the header into a bunch of 16-bit integers, sum them all together, and then take the ones complement, so flip the zeros and the ones, and then discard the datagram if the results don't match. Now notice that because the time to live changes and we're using the header as 16-bit integers, every router needs to recompute this again, which is a pretty significant overhead. So why are we bothering to do this when we already have error checking at the link layer? Why do we have redundant error checking? Well, we have redundant error checking because we are very error averse, and it's much better to not get a misformed packet or to know when we get a misformed packet than to try to process a packet that is misformed. So it is much better from the point of view of the system that all the data that arrives correctly. And so we error check multiple times to make sure that we don't pass any incorrect data along to our applications. Because consider how difficult it would be as a developer if you couldn't rely on the data coming into your program to be accurate, and you had to somehow accommodate for the fact that somewhere along the line a 0 might flip to a 1, and the number that you send is not the number that you receive, or the string that you send is not the string that you receive. That would be extremely difficult to work with. And so we error check multiple times because it's possible to pass the CRC and still have errors. And so we do it multiple different ways, because if we did a CRC here again, well, whatever error we had, it might pass it again because we've done the same kind of math. But now we have two different methods of error checking. It's very unlikely that an error will slip through with 2. Let's see if we need 3 down the road. Keep that in mind. So we've got 2 methods of error checking. Let's see if we need a third. Okay, nobody answered the question on why Ethernet doesn't have a time to live. Well, what are the odds that something bounces around inside of the link layer? Remember, the link layer doesn't really have any routing. If something is sent to broadcast, then it gets to everybody, but then everybody doesn't just retransmit it again. Everything has kind of a terminal destination. And let's say a switch is confused and it thinks that MAC address AAAAA is at port 1, and it passes it along to another switch that thinks that MAC address AAAAA is back at port 1, which goes back to that switch that just sent it to it. That would just be a switch that's malfunctioning, because its switch table at that point would be broken. It's getting a packet whose sender is clearly not AAAAA onto its port. It should realize that that's not the port where AAAA belongs if AA is the sender there. So on the Ethernet level, the odds of a packet bouncing around forever are low. There's no routing, there's no forwarding necessarily at that level to create those kinds of long loops that could give you the possibility of a routing loop. All right, and then at the end, we have the IP address of the sender and the intended recipient, each 32 bits. Unlike MAC addresses, IP addresses are not necessarily globally unique. So remember, each MAC is baked in by the manufacturer. They are supposed to be unique globally. Only one device in the world has each MAC. IP addresses, that's not the case. And we talked about why we couldn't use MAC addresses for addressing. So how do we figure out where everyone's IP address is? Why is IP usable for addressing when MAC was not? Then you've got your options field. The options were basically planned future use. So they thought that there would be some more stuff that would require extra fields. They thought there might be special applications. So they added this options field for the ability to add those kinds of flags and such later. But this ended up complicating processing way too much. And it adds the overhead of requiring the length field in the first place. So this was removed for IPv6. So how come this increases processing? Well, when a router gets a datagram, if it doesn't know how long the header is, it needs to do a bit more math, right? It needs to read that length field, figure out where the options end, figure out where the payload begins. Extra work reduces the time that the router can execute switching, increases the overhead on what is already a very burdened machine. So this was a bad idea in the sense that it put a lot of the overhead where the overhead already doesn't need to be. And then, of course, you've got your data field after that. So remember, that's going to be the payload of the datagram, and everything we learn later on about the transport layer and beyond is going to fit into that field there. So just like everything in the datagram here fits into the payload of the Ethernet frame, everything beyond here is going to fit into that data or payload field in the datagram. So we've got data stuffed inside of data, stuffed inside of data, headers all around. Alright, so let's talk about how IP addresses are distributed in such a way that allows them to be used for addressing and forwarding, much like your residential addresses are distributed in a way that allows them to be used for you to send and receive mail. So we need to allocate IP addresses in a clever way such that they are able to be grouped. And when they can be grouped, then you know that you can send your data along to a particular area, region, etc., and then they can do the more fine-tuned passing along once they get it. That's how mail works, right? But, of course, you can't just group IP addresses regionally. First of all, we'd have no idea how to do that in the 70s. If you'd done that in the 70s or 80s, well, you probably would have given all of them to America and Europe, the only places that had any internet at the time. Of course, there are now way more people on the internet in Asia than there ever were in America and Europe in the 70s, so you would have made a pretty critical mistake in terms of distributing the IP addresses then. There also isn't really a system for adding more. That's one of the problems that we face today, that once you run out, you're kind of out. So if you handed them all out in the 70s, well, then you'd be out. And it turns out that they were pretty happy about handing them out early on. And so a lot of places that got a lot of addresses are actually giving them back as we start to run low on IPv4 addresses. So they're 32-bit. They're typically expressed again as dotted decimal. You omit the zeros, the leading zeros, if you have them. Obviously, we don't usually do that for hex. We usually use standard lengths when we write stuff in hex. But in base 10, it's more typical to omit leading zeros when we have them, so we omit them. And just remember that under the hood, everything is still binary. This is 32 bits of zeros and ones. That's going to come into play in a bit here when we talk about subnets. So for routing to make sense, we need to allocate these sensibly. In real life, that means we use things like states, counties, zip codes. So we try to allocate IP addresses first by geographic location, then by large organizations, and then by other factors. Let's look at how that might work. So in order to allocate addresses intelligently, we need to be able to subnet them. A LAN, a local area network, is typically a network of physically connected devices. We talked about that for the link layer, right? And in a LAN, typically only the router has a public IP address that's exposed to the internet. It's a little bit different at John Carroll, actually. We have so many IP addresses that were allocated to us at some point that actually I believe each of your CSVMs has their own public IP address, which is pretty cool. But generally speaking, only the router has a public IP address, and everybody else shares it. So these devices need their own IP in order to talk to each other and to the router on the network layer, because since they're all sharing the public one, they can't just all be that same address. And this is likened to when you have, say, an apartment building. Everybody shares the same street address, and then you all have different units that you can use if you want to send each other messages or if somebody needs to refer to a specific residence in that apartment. So you have your building address that you all share, and then you have a unit address. Only in this case, we want to give everybody a specific address. We want to give everyone their own street address, even though everybody's technically sharing a street address, because we want everyone to have the same kind of address. We want them all to have a 32-bit IP. So a subnet, which is sometimes just called a network or an IP network, especially by IT folks, is basically just a block of IP addresses that have been networked together and that the router is responsible for maintaining. We can split a network of IP addresses into smaller networks by subnetting them. And a subnet mask just tells you that the first X bits of the IP address on this subnet will be the same. So every machine on the subnet, the first X bits of the IP are going to be the same. You can start to see how this might help for forwarding, right? So if you have a message that's intended for 111.222.333 and then something at the end, right? And you know that all messages that go to 111.222.333 go to a particular subnet. Everybody on that network is 111.222.333 and then the rest. Well, then you can forward the message to that subnet regardless of what the thing at the end is. And that's essentially how all forwarding works. We know that different IP addresses are subnetted, and so you know anything that starts with 111.222 goes here. So all I need to do is get the message closer to that destination. But for example, if your address is 192.168.0.1 and then you have this /24, that means that you are on the /24 subnet. All IP addresses on that subnet will take the form of 192.168.0 and then something else. The first 24 bits are the same. Now, this is a convenient notation when it's a multiple of 8, right? You notice I was able to say .xxx at the end there. Now, if it was 23 instead, then the first 23 bits would be the same. You wouldn't be able to say the third number there, right? So if the first 23 bits are the same, then the third number has which options? What can the third number be? The third decimal point number, if the first 23 bits are the same. It's a confusing question, right? So it doesn't make much sense to address it in base 10 for some folks. I'll let you post the answer to chat if you think of it. What would the third number be if the first 23 bits were the same? So each host would, in the case described above, the /24 case, they would get an address from 0 to 255. So that means that this subnet can support up to 255 devices. And if we expect to have more than that, then we'll need a larger subnet or another subnet. So let's look at a simple example of how you might use that. So let's say that you are an organization. You have a public IP over here of 123.222.111.0.0.0. So this is how the rest of the world talks to you, and only your router talks over that IP. Now, once traffic enters your network, we'll discuss how it gets to all of its individual destinations later on. But that's your public IP, and then internally your router addresses everybody like so. So everybody in sales is on the 192.168.0.0/24 block. So everybody in sales has an address that starts in 192.168.0. Okay, so the first machine in sales is 192.168.0.1, the next one is 192.168.0.2, and so forth. Accounting gets 192.168.10/24. So every machine in accounting starts with 192.168.1, and then the first one has .1, the next one has .2, .3, and so forth up to .5 over here, let's say. So let's say that sales wants to send a message over the network layer to somebody who's 192.168.1. As soon as that arrives at the router instantly knows that it needs to be forwarded to accounting, because that's where the .1s live, right? And any message that arrives that's destined for .0 instantly goes to sales, because that's where all the sales machines live. So this greatly simplifies the amount of table that the router needs to have, because it knows that all of the zeros go there, all of the ones go there. And this is a very, very simplified example. In this case, if you're very careful, you'll notice that there's technically no advantage because all the machines are directly connected to the routers. The only way that this conveys any advantage is if there's also some sub-networking going on there and there. But the point still stands. Everybody is able to quickly determine whether or not an address belongs to accounting or sales. So sometimes people who hate clarity and don't like dealing with the fact that numbers that are not multiples of 8 are not easily expressed in dot notation with IP addresses will use a subnet mask expressed as dot notation instead. In fact, this is probably the more common way to see subnet masks pictured. So instead of the slash notation with the IP address, you'll typically see it expressed like this: 255.255.255 dot something. So going back to my /23 question, Let's find it in the table here. That's 255.255.254.0, because if the first 23 bits are the same, then the 24th one can be a 0 or a 1, which gives you either 254 or 255, right? And that supports up to 510 hosts. Now we've doubled it from 255, technically 254. We actually lose one for the device itself. So technically we've doubled it to 510. Okay, that's because we have all of the devices that we could have mapped on /24, and then all of those again, but with that 1 bit difference. All right, and you continue to do that for every additional bit you change. Now, there is a formula for converting the slash notation to the dot notation and vice versa, and you can look that formula up, and it's incredibly complicated. I encourage you, whenever you need to do it, to simply consult the table. I think it's much faster than trying to work out the formula, especially because dot notation doesn't translate very easily mathematically. It's got a bunch of dots between it. It's very confusing. So I would say whenever you need to translate between slash notation and dot notation, just consult your table. There aren't that many possibilities. You can only go from /8 to /31, and most of those aren't really used. So if you're programming it, you might consider just making a series of if statements or some sort of table. It might be faster than figuring out the formula. It's a little tip for your homework if you're having trouble researching how to do the conversion. So, now that we know about subnetting, how does that apply to the whole internet? So internet service providers, the people who facilitate the internet, get allocated large blocks of IP addresses by the registration entity in their country, which is really by continent, but also by country. So you get allocated a certain number of IP addresses in a subnet. So let's say that a large ISP gets allocated 123.20.16.0. So that /16 is enough to service 65,000 customers. Go back to the table for a second. So it would be double what /17 is. /17 is 32.7, so let's call it 33 and change, or about 33. Double it, you get about 65, right? So we're looking at about 65,000 possible hosts. Each of those hosts is a possible customer for the ISP. So that way, anybody who gets a packet that's addressed to 123.20, and then it doesn't matter what the rest of it is because it's /16, everything that goes to 123.20, those first 16 bits are the same, goes to ISP A. So all I need to know are what the first 16 bits are, and I know that that's supposed to be destined for ISP A, wherever they are. So then I just forward it along to whatever path I know gets that packet closer to ISP A, so that it can get closer to its customer. And then once it arrives on ISP A's network, once it arrives in the 123.20 band anywhere on that ISP's routers, then it decides internally how it's going to forward it. And they might further have subnet their network. We'll look at that on the next slide. Now, a big baller ISP might get a /8 block. Let's say they get 124.21.16.0/8. /8 is very big. That means that only the first 8 bits are the same. The other 24 vary. That means you can service up to 16 million addresses, 16 million customers. So those obviously sell for quite a bit of money, and only a few ISPs in the world still have /8 blocks. Also makes forwarding super duper simple, right? Anything that starts in 124 automatically get that closer to ISP B. So it makes a lot less work for the router. As soon as it sees that it starts in 124, boom, I forward that to whatever gets you closer to ISP B. Simple. So let's say ISP B, who has 16 million addresses, decides that they're going to serve the state of Ohio like this, right? So they own 124.21.16.0-8. That means anything that starts with 124 is theirs. Okay, so the rest of that stuff is just optional, basically. All right, so let's say that they've decided that 124.21.22.0/24 goes to a giant company here in Ohio. So they need a fair amount of addresses, thousands, so they get to be /24 in that branch there. Anything that starts with 2120/12, that goes to the whole state of Ohio. All right, so big place, state of Ohio. So they get a whole /12 branch. How many would that be? Let's see. What's a /12? The last one we have here is a 17. Okay, so a 16 was 65,000 customers, right? So it's going to double another 4 times. That's going to be probably enough to serve the state of Ohio with its 10 million or so residents. And let's say that a /16 goes to Cuyahoga County. Now notice that that is a subnet of the /12 block that serves the state of Ohio. So if the first 16 bits match, you know it goes to Cuyahoga County. If the first 12 bits match, you know it goes to the state of Ohio. So someone that's forwarding traffic to this ISP from, let's say, California will read the first 12 bits of that 124 address forwarded to the state of Ohio. Then once it arrives in the state of Ohio, a router might read the first 16 bits and see, this has to go to Cuyahoga County. And then once it arrives in Cuyahoga County, they might read the first 24 bits and see, this is supposed to go to Company Z and send it to their network. So it used to be that IP addresses were only allocated in /8, /16, and /24 blocks. These used to be called the Class A, B, and C blocks. And so you could only buy or allocate addresses in these units, which was pretty wasteful, right? Because /24 is quite large. If you only need just, let's say, a few hundred, if you're a small organization, then the smallest number you could buy was still a whole /24 block. So now we don't do that anymore. Now we can allocate them more intelligently. We allocate them individually. The downside is that now it's harder to keep that large subnetting, that, anything that starts with these numbers has to go to this region. The regions are able to grow smaller when you're able to buy smaller blocks of IP addresses. So let's look at who the biggest ballers are around the world. Let's look at specifically in the United States. Who has the /8 addresses? So you'll notice most of these were assigned in the early 90s, so in like 92, 94, 95. The first one goes to level 3 communications, now operating, I think, what do they call themselves? CenturyLink, I think, partners with level 3 now. So I don't think we have CenturyLink available as home internet in Ohio, or at least not in our area. But in many parts of the United States, CenturyLink is the primary provider, usually a fiber or DSL. But level 3 owns a very large chunk of the backbone of the internet. So most of the connections between cities and states and countries in North America and Europe, level 3 owns a very substantial portion of them. In fact, so much that when level 3 had an outage, I believe earlier this month or at the end of last month, they knocked out something like a third of the internet for several hours just because level 3 had a routing issue for a few hours. They pushed a bad update and they had a routing issue for a few hours, and they were able to knock out something like a third of the internet, including many customers of existing large-scale hosting platforms like AWS and Cloudflare. They still send their traffic over the backbone that is built by level 3 and others like them. Okay, then of course you have AT&T, which everybody probably knows. AT&T, of course, faced several monopoly lawsuits over the many, many years, and so this /8 block has gone through a number of different ownership changes, but I think it still belongs to AT&T. You'll see Comcast further down on that list as well. So all of the largest ISPs in the United States that were around back then have their /8 blocks from back then. You'll also see some surprising ones like Ford, Apple, and the U.S. Postal Service. A few of the /8 addresses are actually allocated to military use and to the federal government, so those aren't pictured here too, but some of those are allocated to the military and the federal government. And a couple others that you probably haven't heard of, but those are extremely, extremely valuable today. Let's look at how valuable those are exactly. So these are the recently closed auctions. You buy IP address blocks at auction, so you buy those subnet blocks at auction. You buy them in the North Americas from Aaron. And Aaron, A-R-I-N, typically they sell for something between $10 and $25 per address. The bigger the block, typically the more valuable the individual addresses are. You want to buy as big of a block as you can. It makes the routing and the forwarding easier when you have a big block. And so typically those will go for something like, I don't know, 10, 20, 25 bucks an address. Also, sometimes people want a certain block. They want a particular number, and they'll be willing to pay more for it. So let's look at the registration authority by basically continents, although you'll notice that parts of Asia are still included in the European registry entity, so not necessarily by continent as we think of them. And of course, Australia got lumped in there with Asia. And if you zoom in real close on the Caribbean islands, you'll notice some of them get to count as North America and some of them count as South America. So it's a little wonky as to who goes where. But basically, these are the 5 organizations that sell and allocate IP addresses around the world, and they all communicate with one another, so they've all agreed on who gets what, and everybody agrees to follow what they determine and not to just sort of pirate and pretend that an IP address is yours when it isn't, which, if you think about it, is a remarkable level of human cooperation that we've given the authority to these registrars to hand out IP addresses, and that everybody just listens to them, and also that across all kinds of different continents and political systems, they all cooperate with one another. Really cool. So if we look at a map of the internet, this is from XKCD. This is rather old, but everything's still pretty much the same. They've done their best to try to keep the IP addresses allocated in a somewhat geographical way, but they haven't done a tremendous job at it, because obviously they didn't know who would need what when they started them in the 70s, and they sort of allocated them in blocks. And at some point they probably thought, North America will never need more than this many, and then they ran out. And then they thought, okay, the US and Canada will never need more than this many, and then they ran out. And then they thought, okay, here's some more North America, and these will probably run out too. And the green at the time were still available. By now they're probably all allocated as well, or most of them are. You'll see that in the top left corner you have a lot of individual companies. These were, in the early days of the internet, allocated big blocks. So you have places like HP. Remember, we saw that Ford had a /8. We saw Apple had a /8. So these are big /8 blocks allocated to individual organizations at the beginning of the network layer days. And then, of course, you've got your geographical ones all over the place, different Asia-Pacific. You got Europe, other Asia-Pacific, Japan specifically, separated from Asia, Europe, various Latin American, Caribbean. So when you get an IP address that starts with, let's pick a random number. I'm going to close my eyes and pick 70. All right, 70 goes to America. So if I get 70, I know it's going to the USA or Canada. I need to forward it to whatever router gets me closer to the USA or Canada. Let's go with 123. 123 is right here. It goes to Asia Pacific. So I need to forward it to whatever gets you closer to Asia Pacific. Let's say 52. 52. There's 59. 33, 34, 35. I got 51. This font is strange. Is that 52? Let's say that's 52, whatever. USPS, okay, goes to the Postal Service. So whatever router gets me closer to the Postal Service. So while they're not physical locations, and while they're not necessarily geographically done, they are done in such a way that allows you to forward them to where they're going. Here's an alternative map using colors, so showing you also how many are still available and how many respond when pinged, so respond when you attempt to contact them. So most of the ones allocated to the nations and continents and such respond. Most of the ones allocated to individual organizations do not. This is because most of the individual organizations that got those addresses allocated to them, they don't really use most of them. They have a whole /8 block. So Prudential Insurance Company, for example, has 16 million possible addresses. Well, they certainly don't need 16 million for one company, so they don't use them. So many of these organizations have, over the years, either sold or given their addresses back to the registrars. All right, that's going to be it for today. We'll have the network layer lab either Monday or Wednesday. I'll put that on Canvas a couple days before it happens. And probably Wednesday. Probably next time we'll look at DHCP. So thanks for tuning in, guys, and I will see you on Monday.